Thank you so much for having me here. It is such a pleasure for me to be here in France again. So I'm going to talk about my experiences, what I've learned, and how we can borrow some experiences from other fields of engineering. So it's going to be my war stories, happy stories, sad stories. So you're going to hear about those. So this is me. I'm smiling, I'm joyful, but mostly this is my face with relief. Relief because I just finished this part of the climb. So it didn't go so well at first. I don't know if you can see, it's a slight overhang, what we call in climbing, where it's not just straight. There's like a angle, but it's an awkward angle. This is not too bad of an overhang, and my climbing buddy Roger, he took the previous picture. So this is a mountain in Southern California, and it's what we call multi-pitch climb. So you need to attempt to climb in different stages. So you climb certain distance, and then you climb, and so on. So it's a 4-pitch climb. So this is the crux. And so when you're at this point, there is no going back. The only way is up. And if you miss, and I did miss, you dangle on the rope. So there's an old James Bond movie. I can't remember the name, but he's dangling, and he's James Bond. So he takes his shoelaces and then makes a Prusik knot on the rope, and he climbs up, and then, takes care of the villains. So I'm thinking in my head, this actually went through my head. And I'm like, I know I'm not Bond, but I have proper straps. I'm a climber. I have stuff. And I know how to make a proper Prusik knot. So the Prusik knot is you can weight it, and you can stand on the rope, and then it's like a rescue technique. And then you can slowly, when you take your leg off, when you take the weight off, you can slide the knot up. It slides up nicely. So all this is going in my head. How do I get out of this situation? And we had this walkie-talkie because it's my buddy. He's way up on the mountain, and so it's hard to say, hey, I'm stuck. What do I do? So we have this walkie-talkie. In a previous attempt of climbing a different route on this mountain, we thought that would be a great idea, but we had forgotten this concept of channels. So he was on a different channel, I was on a different channel. It was chaotic. I was like, I'm ready, you can start the play, and it's so hard. But this time, this was the second time on that mountain, so we had learned from the previous mistake. So we were okay, we're gonna be on channel 5. And so even if it gets changed, we're gonna, so I set it to the right channel. I'm like, hey, Roger, I'm not freaking out quite yet, but I think I'm getting there. And Roger, he's this guy, nothing phases him. He's a physicist, but he was also learned law because it's fun, and he passed the bar exam. So he's this physicist, scientist who likes law. So this kind of character. And so he tells me, hey, it's okay. It's not terrible. It's just rest up, take your time, and give it your best. Don't just do half-hearted attempts, because I was trying that, and I tried this dangling thing 3 times. And once you dangle, it's kind of a little bit difficult to get back on the climb, because you have to maneuver yourself back on the rock and then try again. So I was okay. And then he was like, there is something for your left hand. If you just reach up, maybe try it, but just give it your best. And so I'm also direction confused, challenged. So whenever he says left, and I'm using my right hand and looking for stuff, and he usually says the other right or the other left. But he's not there looking at me, so I'm telling myself, okay. Proper left, which is the left, double check, and so I tried it, and then I made it. I was like this person here hugging the rock. I literally hugged that rock. And so just for, this is kind of where I was dangling, just for perspective. So this is the Idlewild Tuckheats Lily Rock Mountain, and it's called Trader Horn, for those of you curious about the climb. It's called Trader Horn because when you climb, at first you see this big giant horn like a rhinoceros, and you think, okay, but that's not the real horn. From there you get to see this very awkward thing, which is very exposed, and so you get this like, holy Moses. So, so why is this story interesting? Because I think we can take a lot of lessons from climbing, rock climbing, into how we build our systems. So every aspect of rock climbing, I think, applies very directly to the software systems that we build. So this guy over here, he's John Long, and he's a pioneer of climbing. These days, we've got all kinds of fancy equipments, like we've got these cams, so which can provide this amazing strength or force so you can hang off of. Back then in the 70s, there were no cams. And so these guys were pioneers, and they did the hard way and did first ascents. And so he has written many books. So he came up with a pattern for how you can design these anchors, because when I'm dangling on that rope, it's the anchor system that is protecting me. So every rock climber, if they want to live another day and do more climbing, they pay attention to these climbing principles. So this is called serene. It's kind of nice, serene. You go rock climbing, and so S here stands for solid. When we go climbing, we put oftentimes we put carabiners or quick draws and clip onto these bolts. So we are trusting these bolts, and the safety of the climb is only as good as this bolt. So we're supposed to inspect the bolt and see, is it rusty? Is it wiggling? Because if it's rusty and wiggling, it's probably not a good idea to trust that bolt. So that's the first concept, solid. So we can take this concept, solid, and look at our systems that we're building, and we can see how are our components, how good are they? Are they unit testable? Can we rely on them? Because your system as a whole is only as good as the components that are, helping, forming that fundamental infrastructure of your system. So I worked for this mortgage domain. So I was in this company was taking care of banks and mortgage companies. So they would send us letters or lists of addresses. So basically, if you're a homeowner who did not pay your mortgage on time, there are a set of regulations of what happens. So the bank needs to send a notice. It needs to go out in a certified letter fashion. So there's so many rules according to the state regulations. So and these regulations depend on different states. So different states had different rules. So there was an existing application that took care of this. So the states made new rules that said, like, if you, as a bank, are sending this letter to the homeowner, it's your responsibility to also register that loan information with us, because they're trying to protect the homeowner, because banks can say, hey, I sent them a notice. And so they're trying to protect the people. So they said, like, hey, you have to register with us. And so how you registered was different depending on which state that mandated the law. And there was this existing application. It wasn't great. And so we were looking at, okay, how can we rebuild this? And so I love event-driven architecture. And I was like, we need we need reliability, and we need message queues. And so we can create this beautiful system, so which is loosely coupled, and where registrations for one state is not going to affect the other. So we came up with like this really awesome architecture with auditing and everything. So what happened was, at the midst of it all, was this one component which actually did the registration. And that one was reused for all the states. That didn't change. And that was the problem child that would eat exceptions. So whenever there was like exceptions, it wouldn't bubble it up. It just logged it, and the logs went nowhere. So it was this thing. And so we didn't change that. We deployed this solution, and for a second, it just worked. Like typically, you deploy and then you think, something wrong. Let me look at the logs. And there was none of that. We deployed. Everything worked. We ran through registrations. No errors. The audit log is just perfect. And I'm starting to worry now. Why is this so perfect? And so looking at the message history, there's like all of these messages being orchestrated. Everything looks good. Typically what happens when we submit the loan information is a day later, we would get some kind of acknowledgement from the state saying like these loans were accepted, or we need more information on these loans. So we had to wait a whole day, and then silence. There was nothing. So now we're panicking and looking, and there's no errors. The message thing, the audit log, the history that I took so much care to put in was just all perfect. So then we dug a little deeper, and there was this mode called demo mode. And so what happens is, in this demo mode, you go through pretty much every step of the action except submitting that action to the state. So that never happened. So we had to roll back. Our CTO was not impressed at all. And so the moral of the story is, you can make your car a little bit more fancy, change seats, and make the body look good. But underneath it all, if the engine is like crusty and it's going to die on you any minute, then it's perhaps not worth to spend a lot of time around it, but actually fix the thing that needs love and care. So that is the concept. That is how I take this concept of solid from rock climbing into the things that I'm building. The next thing is redundant. Hey, we climbers like to live so we can climb another day. That means everything, like our life, depends on these anchors. So in climbing, you need multiple points of protection. So these are two. This is a top anchor, and there's two systems. So we will connect like our carabiners and quick draws, and we would double it. Everything is doubled on each side in like opposing ways. So even if like one part of this anchor fails, we're still safe as climbers. And I'm not that great of a climber, so I fall a lot, and I have this like, oh yeah, I'm totally fine. I'm just gonna hang, just gonna take a little breather and climb again. So I get that confidence because of how the anchors are set up. So taking this concept into our software, we can see what are the things that are most critical to our software systems. So it could be the database. A lot of times I worked in systems and it's just one database. What if that database fails? And so we provide clustering and high availability for these important resources. But it shouldn't have to stop only for critical things like your database. There could be some really important services that if you don't provide that service, perhaps the business is losing money. So what about those services? How could we make them highly available so that like one instance goes down, the business as such is not losing money? So the concept of redundancy, you can take that and apply to which systems or services are critical to your needs. This one is equalized. So what this means is sometimes, like when you set up the anchors, if we want to make sure in rock climbing, the weight or the load is equally distributed among these multiple points. Because if the weight is not equally distributed, and if something happens to like one part of the system, it could impact the other part of the system. So we really want to make sure that we take this into account. So we load balance. So like as a software person, I'm like, hey Roger, this just is so cool. This is like John Long just might as well called it the patterns of distributed systems. And so if you look at load balancing, oftentimes we might have a load balancer in front of our web systems to make sure the load is equally distributed. But sometimes we might use things like sticky sessions. And so inadvertently, we might be sending a lot of requests just to one instance. And therefore, like even though you have this load balancer in front of your system, it's still not equally distributed. So that's a problem. So we want to be mindful when we design these systems to see how, especially for business critical services, are we able to support that load? The final principle of setting up climbing anchors is no extension. This is pretty important because when we're climbing, especially if one of the anchors give out, it shouldn't drop the climber. So literally no extension means like it doesn't extend or like drop the rope because the rope is passing through these multiple anchors. So one piece pulls out, and let's say that there's this distance and it just suddenly drops. That can, like especially a climber taking a fall, like on that climb. So I'm taking a fall, and this one piece, let's say it's just not protected well, and that pulls off, and then the rope suddenly drops a little bit, and that's like shock loading the other two anchors. And now, like, the anchor might have been able to take that tension normally, but you've just added that extra bit of shock, and that could just, like, totally destroy you. So this, in software, is the concept of cascade failures. So how can we ensure that the systems that we're building, when it fails, it needs to fail gracefully and it doesn't go and like take the entire system down. So here's the war story. On that same project, I know, thinking back, I'm like, oh my God. So on that project, one of the things that I really wanted to do was we had support teams, we had developer teams and so on. So it was back before the day of DevOps. So it was very, very siloed. And so I was like, hey, if I put a piece of my code in production, I want to be the first person to know when something goes wrong with it. So back in that time, Microsoft Patterns and Practices had this concept of like email alerts and how easy you could just take that and drop it in your code. So you could attach it to your exceptions, and now you can like configure how you want to be emailed. You probably know where this story is going. So you could set up multiple levels of escalation, and so I set that up. And it was good. It was a good idea as ideas go, but not all ideas are great, and I found out the hard way. So what happened was there was a major outage. The database went down. This was the database. So all of the services are connected to this one database. So when things went bad, it was early Saturday, it was 4 a.m., I did get an email, and my phone beeps or something when emails come, so I was crazy. I still am. I sleep with the phone next to me. So I saw this, and I'm thinking, oh my God, the database is down, and I'm sure like the ops people are getting these notifications too. But the trouble is, all these services had a timer in them, so it was like running every minute. So every minute, it's trying to do something, get data from the database. There's an exception. Oh, let's send an email. So now, you've got the database failure, and now all these messages are queued to the SMTP server, like for sending emails. So my poor, and it wasn't just my service that was doing that. We had adopted this thing because we felt it was a cool thing. And so all these services, so it was like an overload of the SMTP server. So our ops people were not happy or impressed with us at all, because essentially we DOS'd our own system, our email server. So these are like interesting concepts that when we think about climbing in distributed systems, designing distributed systems, just a little thought up front of like, hey, how is this going to impact? How is my load going to get distributed? How can what happens when this thing fails? How is it going to get impacted for all the other things that rely on this critical piece? So turns out you can solve this problem if you borrow some principles from electrical engineering. Electrical engineering, by the way, I did do my degree in electronics, so that was my major. I did computer science part-time because that was my love, like my first choice. Electronics was like, let me try to widen my knowledge, but I'm glad I'm still a software engineer. I'm not designing circuits. Let's just put it that way. So in electrical engineering, there's this concept of fuses and circuit breakers. So my brother, he's the electronics whiz in the family, and he's 6 years older to me, so I grew up watching him. He has this whole like graveyard of components and things that he took apart when he took apart radios and things like that. So he always had a little bit of everything. He taught me how to solder. That was so fun, just to melt the lead, which we no longer use these days now. So I learned a lot from him. And growing up, summertime, we used to have these power outages. And so all of our major surges too. So all our major appliances, like the TV and stuff, was connected to this appliance that had a fuse, and this is a 1 amp fuse. And so the fuse has a literal wire inside it, and if there's a power surge, the wire would literally melt, causing disruption in the flow of electricity. So this surge is not going to impact your TV or anything. It brings pretty much everything down. So I don't know what I was trying to watch back then. It was pretty important. I was like, dang, this TV is not working again. Let me troubleshoot. It's like, dang, this 1 amp fuse isn't working. Okay, I can see it's dead. Okay, so now I'm looking around for a 1 amp fuse. I couldn't find it. I go to my brother's things, and then I take a little copper wire and go, okay, that'll work. All I need is like a little bit of connection. I forgot to check the main switch, whether it was on or off. So I got a nice 230 volts electrocution. My mom was like, oh my God, are you okay? And she was concerned, but I was okay. I just learned not to do that again. But my mom would have been more upset with me had that thing worked and the TV blew up. Then I would have been like, done. So in electrical engineering, you can take that concept. So this is painful. Every time you're looking for a fuse, replacing the fuse, you have the concept of circuit breakers. So circuit breakers, our houses these days have them, and they have multiple levels. There's a primary and there's a secondary. If the power goes out in the living room, your refrigerator is still fine, stuff in the appliances in the kitchen are fine. So you have these multiple levels that you can take, and also you don't have to go replacing things, you can just go and reset the circuit breaker. So when the circuit breaker trips, the power shuts down, and then when you think it's safe, you can go and flip the reset switch. So you can borrow this concept. We talked about what happens when the databases fail. That's like a huge failure. That is a very, very important resource. Without that resource, none of your other systems are going to work. So what is the point of keeping these services up and trying every second to try to get data from the database when you know the database isn't available? So you can borrow that concept and model it in your code. You can take that pattern and write code for it. So the two actions are trip and reset. And so you could model this, and you can unit test it, and you can say, how long should I wait? What conditions should I wait for? What is the piece of execution logic I should call in case of this failure? So you could determine what those actions need to be. So you can trip. When you trip, you call this action, and that action could be like, okay, I'm going to shut down my service because I'm useless pretty much without the database. So you can do this, and you can unit test these concepts in your code. So the other thing that you can borrow is from the real world itself. So when you go, like, I live in the US. Unfortunately, Starbucks is like the only coffee shop. Like, I so wish I was here and have amazing croissants and coffee in the morning, but I'm stuck with Starbucks. So when I go to Starbucks, this is not how Starbucks works. You don't go and order a drink, and then the cashier doesn't go to the barista and then waits until they make your drink and come back to you. This is not how it works. But when we write services, we often use this way of working where we make a call and it's synchronous and we're waiting for the results to come back. So this introduces this thing called as temporal coupling. So temporal coupling is this idea that, like, this service cannot do its job unless until the other service is also around providing the service. So we could take the Starbucks model and see, because what really happens when you go to the cashier, you pay for your drink, the cashier takes down, oh, what is it? Oh, you want a cappuccino, or writes your name and the order what you want in a cup and puts it in a queue at the desk of the barista. Same thing. You can have this component that receives a message and processes that message and puts another message on the queue for a different part of the system. So this way, it's completely decoupled. Now you've got two services. They're communicating using events on a queue, and because these messages are durable, even if one process dies, like let's say the barista process dies, it's fine. Just like the barista in real life might have shift changes and go away. But nothing happens to those cups there in the desk. So whenever the new barista comes in, they just start processing the message. Same way, these messages are durable, and so when the new service comes back up, we can process these messages. So you have that, and also they're completely decoupled, and you can scale the barista service differently. And if there's a really long line, then you can have like two cashiers taking. So how you scale also becomes a lot easier when you start introducing event-driven and message-based queuing style architectures. And then control systems. Everything that we have working today in our homes and everywhere is based on control systems, like cruise control in cars, refrigerators, the thermostat in the house. Everything is a control system. There's two types of control systems. This is the open control system, where it's manual. So here, like, you can think of camping. You're cold, so you start a campfire, and the fire's burning down. You have to make a manual action. Oh, I need to go in, because the temperature is getting colder. Manually bring those logs and dump it in the fire to keep it going. It's a manual action. So this is an open loop system. And then you have like these thermostats, which is a closed loop, because the feedback of what your current temperature is, you've got sensors that's measuring, and that feedback is passed back into the system to decide what we want to do. So So there's three things that's going on. So you've got the current value, the measured value, what it is, and what's your optimal temperature, and what's the difference between like what it is right now and what your desired value is. So how this error conditions are, so control systems is this science of like mathematical. So if you ever wondered, like, why did I learn differential equations and calculus, this is where it's being used. So all of this mathematics play in a role in, because if you just go off of proportional rate changes, then the system is not going to be super stable. Your AC is going to act wacky. It's going to go off, on. That would be crazy. So you want a stable system, and that's where control systems do this. So one thing I wanted to mention about control systems is like companies like Amazon, they're really looking at, so they have like a PID controller. PID is proportional, integral, and differential, I think. And so you combine these three mathematical models to build a stable system, and they are using that. Like, so for users, we have this slider saying like, okay, after this, like, automatically scale up my instances. So you have the auto scale options. So when those sets of variable changes, they're like looking at all these different things in order to say, okay, I'm going to spin up 5 instances for you. So they do use this concept. So you might not need to use this in your models, but I think this is just a really nice way of thinking and trying to borrow, especially from other disciplines. And lastly, the point of like building amazing architecture, we want it to scale, is ultimately going to serve our humans, like our users. So we need to put in the thought at every step of the way when we're designing these systems, is this serving our user needs? And this is where we have concepts like domain-driven design. I think Suzanne yesterday talked about building adaptive systems and using different principles like Wardley mapping and domain-driven design. So domain-driven design fundamentally tells us, hey, focus on the behavior of the business when you're modeling things. You want to constantly see how the business needs are, and we want to use the same language as that of the domain when we're constructing our contracts and messages. And so we want to be able to speak the same language as our domain experts. So we're not mentally translating things in our head, like, hey, display wait, that means this particular model. So let's just use the ubiquitous language used by the business in our code. So it also pushes this strong sense of collaboration, especially between software engineers and leads and the business users themselves. So we have a very fundamental idea of what is this behavior of this business and how can we model this in our code? Because if we do, then whenever there's a new requirement from the business, then our software, it's easier for us to like align and keep adding this value to the business. And businesses exist to serve the needs of humans. So ultimately, we are taking and serving a purpose. And so it's just being really, really thoughtful about the intention of how is my user going to react to this. And so there's several ways. It doesn't just mean looking at it from the user interface perspective, because that's not the only place the user is interacting. It might start there, but internally, let's say the user interface is talking to APIs, and those APIs are talking to other APIs, and it's taking a while. That also impacts the user experience. So it's not just at a high level, like, oh, this is the screen, it stops there. No. you can take it deeper into your systems and see how these have a really big impact. I'm so sorry to bring up the trauma of Notre Dame. I'm really sorry. But when this happened, I was not working at New York Times, and I read this exclusive from New York Times, and it just blew my mind. So the person who was monitoring the systems, I think he was like 3 days old or brand new on the job, and he's working there, and his job was to monitor in the control room, see what's happening. And he had done the previous shift, but the person that was supposed to relieve him didn't show up. So he's there trying to do a second shift. And then he gets this message on the screen. So now that person's trying to figure out what to do. Oh, there's a fire alert. And so he calls the guard, and I think the protocol was to actually go and confirm the fire first before calling the fire station. So they go, and this error code is fire, and then the next part is broken down into a zone, so it kind of tells you which zone is this fire. You've got these numbers, and there's this aspirating framework. So it had taken 6 years to build this system, and the system was so sophisticated. They had these aspirating tubes, so it sucks up the air and then detects how is there smoke. So it was designed to do its job really well, and that was a very complicated system, and it had taken 6 years for that system to be put together, tested. And so these 110, 315 is probably talking about which of those sensors had failed in that zone or in that region. And this is the aspirating framework, so it detected the smoke. But unfortunately, this was not clear, and they ended up going to the wrong part of the church, the wrong attic, and realized there's no fire. And then when they realized, yes, there was a fire, but it's in the main attic, a lot of time was lost. And when the firefighters arrived, it took a heroic effort to try to save the church. And it was really a super heroic effort, because when the system was designed, there were some risks. Because the wooden lattice is like one of a kind, they wanted to preserve the sanctity of that wooden lattice in the church. And so, and also there's this stone ceiling, and the wooden lattice is above the stone ceiling, and that's where the fire had happened. So it's very hard for the firefighting men and women to try to get the water up. They had to go up a winding stairs of, I think, 300 stairs to go up to try to battle the fire. And some of them did so knowing that they may not come back. It truly was a heroic effort of how this church was saved. And they had, I think when they had designed the system, they had decided not to include firewalls. So firewalls kind of contain, so they prevent the fire from moving from one area to the other. There were no sprinklers and no firewalls. So when this happened, it was just a huge, sad thing. So these were the constraints, but ultimately, it doesn't matter how good your system is designed. If a human at the end of the other end can't make sense of this code, then the whole system fails. So ultimately, everything that we do is for humans. So we might have amazing observability and metrics in our code, but how actionable is the data that you're relying on? When they designed this system, had they spoken with, hey, who's going to be monitoring this system? Can you tell me where the fire is looking at this code? No, you can't? Okay, we got to go back to our drawing board and see how can we make this error message more meaningful to prevent this catastrophe? So I think that it is important that as software designers and engineers, it's our job to take the risks, the constraints of what we're dealing with, and put the user right in the center and see how our system is impacting the user. And I want to leave you with this quote from John Long. Our systems are there to help us. We shouldn't be expecting miracles from the systems that we build. Thank you so much.